for example, you can model a chemical change. This particular chemical change is the reaction here is the hydrogen. Let's see. Let's move over this way a little bit and see if we can see this. It looks kind of confusing. I'll break it down for you. But it's the hydrogen combining with oxygen to give water. That's the chemical change. Okay? And as it's written here, is it balanced? Let's see, 2, 2. No, it's not balanced. So you have to balance it by putting a 2 in front of the water and a 2 in front of the hydrogen. So that's a balanced chemical equation. So you can say 2 moles of hydrogen plus 1 mole of oxygen will combine to give 2 moles of water. All right, and so one way to predict, whether or not a reaction is going to be exothermic or endothermic, and not only that, but about how much energy is going to be absorbed or released upon the chemical change, is to think about breaking all of the bonds of the reactants and forming all the bonds in the products, and looking at the difference in how much energy it took to break versus how much energy was released when the new bonds were formed. And if that difference is a negative difference, then you're going to have an exothermic reaction. And if it's a positive difference, remember, then it's going to be an endothermic reaction. And so in this case, you have the reactants. This might be like an increase in energy here along this way, and this is in kilojoules. And in this way, we have the reaction path going, similar to the little thing I drew at the beginning of this lecture. So say this is the reaction, the progress of the reaction progress or path. And we're starting here with reactants, and we're going to end up here with products. So I can tell by the way they drew these lines, I expect this to be, endothermic or exothermic. The reactants are starting at a higher energy than the products, so I'm going to expect that this is going to be an exothermic reaction. And the way they calculated that was using bond energies. So you're just going to assume that when this reaction occurs, all the bonds of the reactants are going to break, and that's going to take a certain amount of energy. Energy is absorbed. That's what this is showing us. It's absorbed. When you go from the reactants as molecules to the broken up atoms where the bonds are broken, it's going to absorb. Breaking bond energy is the amount of energy it takes to break a mole of bonds. And then when you go to form bonds, energy is always given off. So in this case, the bonds that need to break are, you have hydrogen, and you have 2 of them. And you have oxygen, you have 1 of them. Okay, and oxygen is held together with a double bond. And then you have water that's formed, and 2 moles of water. So if you model your reaction that way, then you can see that if you just assume all these bonds are broken and all of these bonds here are formed, you can do a little accounting of how much energy does it take to break each one of these, a mole of each one of these, and this double bond. And here what we know is from experiments that it takes 436 kilojoules to break 1 mole of HH bonds, and since we have 2 of them, see 1, 2, it's going to be 2 times that, so it's going to take 872 kilojoules to break the HH bonds, which is going to take us up in potential energy this high. Then we're going to have to input another 498 kilojoules of energy per mole to break the OO bonds, double bonds. That's going to take us all the way up here to this energy level. Then when you form HO bonds, and we have 1, 2, 3, 4 of those HO bonds, it's 467 kilojoules per each one of those bonds is released. We have 4 of them, so that's a release of 1,868 kilojoules. And since it's a release, we put a negative sign to it. So we add up all these numbers. 872 kilojoules plus 498 kilojoules minus, or you can say plus a negative 1,868. That gives you a net change of negative 498. So you could estimate just based on bond energies what the heat of reaction should be if you actually do a reaction. Okay, and it's going to be negative 498 kilojoules per mole of methane broken. All right.